Hello and welcome back. Today I want to continue talking about amplifier classes by looking at what class B and its cousin class AB operation means and how these can be implemented in a practical circuit. Today I will be focusing on the theoretical aspects and simulations to observe the various methods in which these operating modes can be implemented. So if you're curious, then keep watching. So, first things first, the definition of class B operation refers to having a conduction angle of 180 degrees. So, only half of the signal is being amplified. This is done primarily in an effort to improve efficiency, and not just the maximum efficiency of the amplifier, which in theory can be 78.5%, but also the standby efficiency. So, as we've seen last time, the class A amplifier has a power consumption roughly independent to whether there is a signal passing through it or not. Now, class B, on the other hand, is completely different. Now, the main idea behind this operating class can be better observed if we look at the transistor response curve with collector current and base emitter voltage. So, the transistor has three operating modes. You've got cutoff mode, no current passing through the transistor, linear mode where you have direct amplification, and, well, saturation. And in class B, the static operating point, so where the amplifier stays when there is no signal, is put right on the border in between cutoff and linear mode. And what this means is that when you're applying an input signal, half of the signal is in the linear mode, it gets amplified and it goes to the output of the amplifier, whereas the other half is in the cutoff region and nothing happens to it. So only half of the signal passes through the amplifier and gets amplified. Now, the main advantage of doing things this way is that the static operating point is in a region where there's no collector current. So the standby current of the amplifier can be made to be extremely small. Current consumption only increases when there is an input signal. And this current consumption isn't just dependent on the presence of an input signal, but it's dependent on the amplitude of the input signal. So the larger the input signal is, the higher the currents that will pass through the amplifier. So current consumption is strictly related to the signal amplitude. So this sort of amplifier is far more efficient from an energy consumption point of view, especially when non-constant amplitude signals are being amplified. Now, as previously stated, the class B amplifier amplifies half the signal. What about the other half? Well, there are multiple things that can be done. In the interest of using a minimum number of amplifying elements, one method of providing the missing signal is by using a high qfactor resonance circuit. So, what I have here is a circuit that looks like a typical class A amplifier, using a transistor in common emitter amplifier mode. So we got our emitter resistor, a voltage divider to bias the transistor, but to test it out, I specifically set the input signal to have an initial delay. So if we run the circuit and we look at the input signal, we can see that it stays low for a while and then the input signal appears. And I've done this specifically to look at the current running through the transistor. So if we check the collector current, in the period when there was no input signal, it was at a very low level, so 300 something microamps in this case. Then when the input signal did appear, it jumped up to 20 something milliamps, so completely different ranges. Now when the signal did appear, so on top here I have the input signal, we can see that the collector current was rising for almost exactly 180 degrees of conduction angle. So I marked out here half of the input signal, and this is where the transistor is actually amplifying. Now, since there's a resonance circuit involved with this amplifier, if we check the output, we can see that it didn't instantaneously reach the full level. So it takes the time it takes to build up the output signal. So this sort of circuit does not have an instantaneous response on the output in reference to the input. And now you may be thinking, well, why use class B operation when you could use class C operation for this sort of circuit? Well, there's one really important aspect here to consider. This sort of amplifier has an output signal proportional to the input signal. So even though the amplifier amplifies half of the input signal, it does amplify it in a linear proportional way in reference to what's on the input, and then the other half of the signal, the unamplified half, is provided by the LC circuit, which will provide the mirror image of the initial signal. So we can check this exact proportionality by using a set of measurement statements. So this is the exact same circuit as before. It's just that the input signal now has different amplitudes, so ranging from 0.1 up to 0.7 in steps of 0.1. And to measure the exact gain of the circuit, I added this bottom set of measurement statements to measure the output peak-to-peak voltage, input peak-to-peak voltage, and then to calculate the voltage gain by dividing these two. So if we run the circuit, we can look at the output, we can see the multiple signals. So as the input signal increases in amplitude, so does the output signal, and we can get a far better view of the exact ratio by looking into the error log. So here if we check the gain, so first one is for a signal of 0.1 volts, and the last one is for a signal of 0.7 volts. Now we can see that they're not all identical, so it varies from 3 to 11, but we can also see that for relatively large signals, so starting from 0.3 up to 0.7, gain is almost constant. So Class B amplifiers have a bit of a problem with small amplitude signals, but we'll get back to this a bit later. Now another set of measurements that I added refers to the efficiency of this circuit. So again, to measure the power delivered to the load in reference to the power taken from the supply. And again, if we continue through the measurements, we can see that, well, we start up with a horrifically bad efficiency of 0.5%, but then we end up with 55 point something. Now, these are all lower than the 78.5% theoretical maximum that you can get with Class B amplifiers, but one of the interesting things that's important to notice has to do with the input power. So one of these measurements refers to how much power is drained by the amplifier, and we can see that for very small signals we have a very small power drain, and this power increases with the input signal's amplitude. Now, final thing to mention about this sort of setup is that since it uses a LC circuit, its bandwidth is limited. So first of all, this LC circuit needs to have relatively high qfactor, and secondly, the amplifier will only work within a restricted range of bandwidth. So even though this works in Class B, this particular implementation is a narrow band circuit, with all of the limitations that it comes with. Now, the more common type of Class B amplifier that you will see though, is one in which both halves of the input signal are amplified. And there are two main ways to achieve this. One of them being the use of complementary transistors. So to have a pair formed from an NPN or N channel and the PNP or P channel transistor. Both of these having similar gains. And the idea behind this amplification scheme is that you take the input signal, split it into two paths, pass them through the two amplifiers, and based on the amplifier type, only the positive half or the negative half will get amplified, the other half will be ignored, and finally, the two halves need to be recombined to form the final output signal. So this way the output signal is a copy of the input signal, but it's amplified. Now this approach is quite common in low frequency discrete amplifiers or with operational amplifiers, but it does have the major downside that you need two very well matched transistors of different types. So you need both the NPN and the PNP transistor to have similar gains and similar behaviors with the input signal. And this is not always easy to achieve. So one implementation of such a circuit looks something like this. So we have a set of complementary transistors, an NPN and the PNP. We have the input bias point set with a pair of resistors, so this is half the supply voltage. And then we simply apply an input signal through a capacitor, and then this goes out for another capacitor into the final load. Now, if we run this, we can see our input signal and look at the input current. So before the input signal appears, we can see that we have almost no current drain, so this 500 microamps is going through the resistors, more than through the transistors. But if we check the output signal shape, we see that it doesn't look like it's supposed to look. So we have these glitches here in the middle. So these are not present on the input signal. So what's happening here is that to actually drive the transistors, you need 0.7 volts for bipolar junction transistor to, well, drive the junction. So from our input signal, we're cutting off this 0.7, and only when the input signal is larger than that, does the transistor actually start to work. So that is why we're getting these glitches here. Now, what this also means is that if we now check the currents and maybe invert one of these, so these are the collector currents for the two transistors, we can see that we're not really getting 180 degrees of conduction angle. So there is a period when no transistor is conducting. So technically, this sort of stage is running in class C, so we're below 180 degrees. But anyway, the way to fix this is to provide the missing 0.7 volts permanently to the amplifier stage. So an implementation that looks something like this. Here, other than the transistors, we also have a pair of diodes through which there's always a current passing, so there's always a voltage drop on them. And this way, whenever there's a input signal applied, the voltage applied to the transistors will be the input signal plus what is on the diodes. So if we run this circuit, so again we have a nice input signal, and if we check the output, well, there's still some distortion here happening in the middle, but it's far cleaner than before. Similarly, if we check the collector currents, invert the second one, zoom in a bit, now we can see we have proper 180 degrees conduction angle. So half the signal is passing through one transistor, half the signal through the other. So to get the minimum amounts of distortion, you need to provide this missing polarization voltage. Now, the other main method to amplify the full signal is a bit more complicated, but it does provide the advantage of using the same type of transistor. So with this method, we can use two NPN transistors. And we only need to do a bit of phase shifting. So the idea here is that we take our input signal, pass it unaltered to one of the amplifying elements, and then we create an 180 degrees phase shifted version of our initial signal. So now we can take the same type of transistor amplifier, amplify the positive halves of the input signal, so we have both halves now, and then with a bit more phase shifting, reinvert the second signal, and then combine the two amplified halves to form the final output signal. Now, the main advantage of this setup is that it's far more easier to find two transistors with matching characteristics if they're supposed to be identical to begin with. And typically, all of this phase inversion is done with transformers, although other methods can be applied. And this sort of setup is most common in high-frequency circuits, or whenever there's no PNP equivalent of your initial transistor. So for example, in things like vacuum tube circuits, where there is no PNP. So one common implementation involves the usage of center-tapped transformers. So something like this. Now, it looks a bit complicated, but I'll walk you through it. So in this circuit, the phase inversion is done using transformers. So both on the input and on the output side. So we can quickly check this. We get our input signal. One transistor receives an inverted version, the other receives a non-inverted version. Both of these transistors will now amplify only the positive halves. So if we quickly slide these down, we can look at the collector current. So Q5 corresponds to this transistor 1. So when this has a positive voltage, Q5 is amplifying. In a similar fashion, the other transistor is amplifying when the other signal is positive. So both transistors, NPN transistors, amplify positive halves of the signal. Then if we look at the collector voltages, so again, each transistor amplified only half a signal. And then these two signals, which are phase inverted, are then finally recombined in the output transformer to form a single output waveform. Now, other than the transformers and the transistors, you have this set of resistors here with a capacitor to set the static bias point. And as you can see, it's set a bit too low, so that's why you have all this distortion at crossover, so when the signal goes through 0, but this can be adjusted. But the major advantage of this circuit is also its major downside. So these center tap transformers. Now, these are not really common components. You can't really buy this sort of thing. You have to specifically make it for your particular application. And that's the downside. The good thing about this is that you can use any sort of turns or impedance ratio. So using this sort of transformer, now I have all three inductors of the same value, but you can use any turns ratio you want. So you can go from high impedances to low impedances, or any way you see fit. So these sort of arrangements were quite common in older transistor audio amplifiers, or at least the output stage is built in a similar fashion in vacuum tube amplifiers. Now, one thing that you could do to simplify the design a bit is to start getting rid of this sort of transformer in favor of a bifilar two-winding transformer. So the first design to look at is this one. Here the output looks exactly the same, but on the input we no longer have a complex transformer, but rather one with only two windings. So the idea here is that the two transistors have the same impedance anyway, so you can sum the two impedances up, and that is what impedance the input signal will see. So in this circuit we have our input signal, so this one, and then one path will see the exact same signal, but the other half will see an inverted version. So through the transformer, a 180 degrees phase inverted signal is generated. These two signals will pass to the transistors, and we get the two halves amplified through the two transistors and then recombined just like before. So we did simplify a bit the input side, so we only have a two-winding transformer this time, but we did complicate things a bit by adding some DC blocking capacitors and some input fixed value resistors. Now, we can also take a similar approach with the output side. So another design to look at looks something like this. Here I left the input side the same, so with this two-winding transformer, but then on the output, rather than having the previous transformer, I used again two double-winding transformers. So here one transformer is used to supply the two transistors, and the two windings are wound in opposing directions. Then the two signals are then recombined using another transformer, so similar to the way in which they were split up on the input side, and then this goes to the output. So if we look at this circuit, so let's start off with the two signals in the two transistor bases, so this blue and orange one. We can see the two opposing phase signals in the two transistor collectors, and of course the two currents, so only one transistor is conducting for each half signal. And now we can look at the two voltages in the collectors and what is on the output. So the output takes the two signals, combines them into a final output signal. So this has double the voltage amplitude of the two standalone collector voltages. So these are about 16 volts, whereas the output is almost plus minus 16 volts. Now there are all sorts of other arrangements that can be done other than these three that I've showed you, but especially when working with high frequency signals, this sort of one-to-one bifilar transformer is far more common, and this makes slightly cheaper designs. Now the final thing to talk about is the difference between class B and class AB operation. So technically there's no constructive difference between the two. The difference lies only in the conduction angle. So class B has exactly 180 degrees of conduction angle, it amplifies exactly half of the input signal, whereas class AB has a bit more than 180 degrees. So it amplifies more than half of the signal. Now the reason for needing class AB operation lies in the way in which the amplifying element, the transistor, transitions from cutoff mode to linear mode. So what I have here is the collector current and base emitter voltage graph that we've used previously, and if you zoom in on it a bit, then you'll see that the current, as you start applying voltage, doesn't instantaneously reach a high gain region, but rather there is a slow transition to it. So from the point in which you start getting a collector current up until you reach maximum gain, you still have about 100 millivolts of base emitter voltage needed. And if you're applying your signal right here at the beginning, so when the transistor starts to conduct, well, this initial bit will not have enough gain, so it will highly distort your signal. So even though you're applying a nice sine wave, right at the beginning you will see these elements of distortion that we've clearly seen until now in our simulations. And well, if you apply the same principle on the second transistor, well, you'll get the same kind of distortion right here where the input signal crosses the 0 volt point. And the solution to this comes in the form of moving the static operating point just a bit higher. So this way each piece of the amplifier amplifies more than 180 degrees, so it amplifies its own half and a bit of the other one. So the output will still look something like this, but when this green output from the second amplifier gets shifted a bit to the left, then you have a bit of overlap. So none of the amplifiers by themselves have enough gain, but combined they get to a high enough gain to allow for a seamless transition from one amplifier to the other. So when two transistors are running in AB class, because of the overlap in the amplified signals, you should get a far more linear and clean output signal. You will, however, be sacrificing a bit of efficiency, but it is what it is. So the only difference between operating in class B and AB lies in the exact bias point with which you drive the transistors. So for this example, I took one of the previous circuits to play around with. So this is the circuit in which we had the two transformers with center taps, and the only thing that I modified is regarding this bias setting resistor divider. So the top resistor stays the same, 2.2 kilo ohms, but the bottom resistor, I go through three values, so 100 ohms, 150 and 200 ohms. Now if we run this, the reason why I did this can be observed in the voltage present in the resistor divider. So on the one side we have 400 millivolts, so with 0.1 kilo ohms. This is well below the voltage needed to drive the transistor. Then the second one is about 600 something millivolts, so just on the threshold to start conduction. And the third signal, 800 millivolts, definitely enough to start the transistor conducting. So the outcome of this is that if we look in the collector of the transistors, so I have the same input signal where it delays a bit and then it starts off. So what we can see is that for two of the signals we have almost no static current, but for the third one we have almost 20 milliamps. So even though peak currents reach 140 or something, so very high values, the static current is completely different in the three resistor value configurations. And the outcome of this can be observed on the output signal. So if we zoom in a bit, we can see that for the version in which we had 100 ohms, so this orange line, we have clear crossover distortion, so when the signal goes through zero, part of it gets lost. It's needed to drive the transistors. Then with the blue line, so this is when we had 150 ohms, it's almost better. It's not perfect, but it looks far more okay. And then in red, so when we had 200 ohms, we have an almost seamless transition. Now, we can see that the third version has much cleaner signals, and the main reason for this comes from the conduction angles. So now I took the two collector currents, and if we have a look a bit, so the colors are a bit overlapping, but we can still make them out. So these smallest currents are coming from the smallest resistor, and we can see that there's a clear region in which no transistor is conducting, so clearly lower than 180 degrees of conduction angle. The second lines almost touch, so these are almost exactly 180 degrees of conduction angle, proper class B operation, which is providing distortion. And then the last currents have a clear overlapping region. So this is what class AB looks like. So constructively, they're all the same thing. It's just that the bias point is set slightly higher or lower. In the end, the class B amplifier offers the benefit of better efficiency, especially with small signals compared to class A, but also it provides the possibility to amplify wideband signals or complex modulations. This is obtained by sacrificing linearity, and the compromise therefore comes in the form of class AB. So this has more static current, but less distortion. It may be worth pointing out that a modern-day operational amplifier running in class AB can have distortion levels below 0.01%. But in the end, the main non-linearity source for both AB or B amplifiers is that the signal is amplified by different amplification elements. You will always have some sort of mismatch between two different transistors. Last thing to do though is test out such a circuit. But that is a topic for next time. For now, hope you got some useful information out of this. Leave your thoughts in the comments. Thank you for watching. Make sure to subscribe to be up to date with all my latest videos, and see you next time. Bye bye.